Here's your introduction to ionic bonding, and starting with ionic compounds. First of all, I want to clarify that you do not call an ionic compound a molecule. Molecules are for covalent only. We call ionic compounds either just ionic compounds, sometimes they're called salts, sometimes they can be called formula units, but they are never called molecules. And the chemical formula for an ionic compound will always represent the simplest ratio of the ion types. So when we were talking about covalent compounds, probably one of the most easily recognizable covalent compounds is glucose, C6H12O6. Well, this obviously is not the simplest ratio of these elements to each other, and that's because molecular compounds, covalent compounds, they don't show the simplest ratio, they show more of a structural formula, whereas ionic compounds don't do this. They are written in the simplest ratio. So we will always, for like sodium chloride, it will always be NaCl, not Na4Cl4. You would always reduce ionic compounds down to their simplest ratio. Ionic compounds are made up of ions, specifically anions and cations. And we'll talk about those more in just a second. So ionic compounds are combined so that the positives balance out the negatives, because ionic compounds are neutral compounds. They are all crystals, and they are all solid at room temperature. And then the formula of the ionic compound does depend on the charges of whatever ions are combined. And we have two ionic compounds down here. This one is sodium chloride, which is just NaCl, and this one is copper 2 sulfate. And this one is a hydrate, and we'll talk more about those later. But this is a copper sulfate crystal, and it's very pretty, makes a really pretty solution. So how do you know what the formula is going to be for a particular compound? Well, you know that the positive has to balance out the negative. And the easiest way to do that is to use what's called the crisscross method. So what does that look like? Well, let's do an example using aluminum oxide. Well, aluminum is a metal, and it is in group 13. And all of the metals that are in group 13, when it forms ions, will form an ion with a +3 charge. If you're unsure about the reason for that, then you need to watch the oxidation numbers video where I explain how you find the charges for different elements. And then oxygen is in group 16, and whenever non-metals in group 16 are bonded to metals, they'll form a charge of -2. Now don't worry about why I put the sign after the number. At the level you're at, it doesn't really matter. If you continue on and you take some upper level chemistry classes, you'll learn the difference and why the sign comes before or after. But here it doesn't matter. If you want to write -2, that's totally fine. So what is the crisscross formula? Well, the easiest way to get your charges to balance out is to simply swap the numbers and say that you have 3 of the negative guy and 2 of the positive guy. And the charges, not the sign, just the charges, will crisscross down and become a subscript on the other element. And here's why it works. Remember, we want to have the simplest formula for our ionic compound that balances out the two charges we're dealing with. Well, in math, to get these two guys to work out to be the same, we would use what's called the least common multiple. Well, what's the least common multiple of 3 and 2? Well, in this case, it's 6. And since aluminum has a +3 charge, to get a +3 to work out to be a 6, we'll need 2 of them. 3 times 2 gives us 6. And oxygen over here is a -2, and to get 2 to work out to be a 6, we have to multiply it by 3. Well, you could go through this least common multiple math every time you write a formula, or you can simply swap the charges and crisscross down to become a subscript on the other element. Well, what happens if instead of aluminum oxide, let's say you had calcium oxide? Well, calcium is in group 2, so that means it's going to form a +2 charge. Oxygen, still in group 16, still going to be a -2 charge. And you'll notice that the values of the charges, not the signs, but the values of the charges are already the same. And so these guys already cancel each other out. But let's say we were just going to go ahead and do a crisscross method anyways. Well, the 2 on the calcium would crisscross down and become a 2 on the oxygen, and the 2 on the oxygen would crisscross down and become a 2 on the calcium. And so we would have Ca2O2. But if you remember what I said earlier, ionic compounds are written using the simplest formula, and so these 2's can simplify down and just become CaO. So what is it that allows an ionic compound, an ionic bond, to form? Well, we got some attractive forces. The main attractive force is between oppositely charged ions. So you have the cation is very attracted to the anion. And then you do still have some of that adjacent attraction going on, where you have, here is the nucleus of one atom, and here's the electron cloud of it. It's very lopsided. Deal with it. And here's the nucleus of the other atom and its electron cloud. And so you are going to have some attraction of this nucleus to this electron cloud. But it's a very minor attraction. And then the same thing here. This nucleus will be attracted to this electron cloud. And these attractive forces have to overpower the repulsive forces. And the main one is from adjacent like charged ions, and I'll show you some pictures in a second where I can explain this better. And then you also have these electron clouds are going to repel each other. So here's a picture of a crystal lattice, that's what this shape is called, of an ionic compound. And you'll see here are the little lithium ions. This is a ball and stick model, and this is a space filling model, and I labeled this one because I figured it'd be easier to see. But it's 2 representations of the same thing. And so this is the fluorine ion and this is the lithium ion. And there is a big attractive force between the lithium and the fluorine. Big time. But there is a repulsive force between adjacent fluorines because they have similar charges, just as there is a repulsive force between adjacent lithiums. Kind of think of this as a 3D model as best as you can. So the way that a bond is made is there's a distance, this perfect distance that is reached, where these attractive forces are at their maximum that they can be, while still balancing out and attempting to reduce these repulsive forces that are existing between adjacent ions. And ions will minimize their potential energy by combining in this way, and this is called a crystal lattice, and you guys do need to know that word. Ionic compounds arrange themselves in a crystal lattice formation. And there's a lot of different things that will determine what the specific lattice pattern is. And the 2 things that I want you to know are the charges of the ions, because that determines how many ions are going to be present, and then the sizes of the ions, because bigger ions, logically, need more space. And so charges and size, that's the 2 things that you're going to need to know. So how do we determine how strong a bond is? Well, that's done with something called lattice energy. And this is the technical definition for lattice energy, and yeah, you need to know it. It's the energy that's released when gaseous ions bond to form the ionic solid. But no one's ever really going to deal with gaseous ions in a lab. So this is just kind of this definition. It's an art. This is how the energy was determined, but nobody actually does this anymore. Now you just look up the lattice energy in a book somewhere, or I guess online. Please, not Wikipedia. And then the larger amount of energy that's released when the bond is formed, the stronger that bond is going to be. And what determines how strong a bond is going to be? Well, if you transfer more electrons, or you can nuzzle up closer because you're a smaller ion, well, that's going to lead to a stronger bond. So here are a couple of examples, and I'm just going to write some of the oxidation numbers on these elements so you can see these lattice energies kind of pop out at you. Well, sodium is always going to be a +1 charge. Calcium is always going to be a +2 when it's in an ion. So this calcium's a +2, lithium's a +1, magnesium's a +2, and potassium is also a +1. And this is all just based on what group they're in. And then looking at what it's bonded to, halogens are always going to be a -1. The group 16 elements are always going to be a -2. And I think that's everyone. So I want to point out here that look at sodium chloride compared to sodium bromide. Sodium chloride has a slightly larger lattice energy. And the reason for that, the two sodiums, they're the same size. But comparing chlorine and bromine, chlorine is a smaller ion than bromine, and so because it's smaller ions, larger lattice energy, because the sodium and the chlorine can nuzzle up closer together and form a stronger bond. Now I want you to compare, let's do calcium fluoride and calcium oxide right here. So calcium is a +2, fluorine is a -1. Right here, calcium's still a +2, but now oxygen's a -2. And so the more electrons that are transferred, basically the higher the oxidation numbers of the elements that are bonding, the stronger the lattice energy. And if you compare these two, you can see that. The calcium fluoride has a weaker bond energy than the calcium oxide. And it's because the calciums are the same, but oxygen has a higher charge than fluorine. So in each of these following compounds, identify the one that's got the higher lattice energy. So I'd like for you to pause this video, try to attempt some of these on your own, and see what you can figure out. So on this first one, we have potassium chloride. Potassium's group 1, so it's a +1. Chlorine's a -1 because it's in group 17. Calcium is going to be a +2, and sulfur is going to be a -2. Now, if you look at these, they're all on the same row in relation to each other. So like the potassium and the calcium are same row, chlorine and sulfur are the same row. So because this guy has got higher charges and more electrons being transferred, it's going to have the higher bond energy. So this one has the higher energy because of charge. Now looking at this one, we have lithium fluoride, sodium chloride. Lithium's a +1, fluorine's a -1, sodium +1, chlorine -1. So they all have the same charges. The lithium and the sodium are both +1, the fluorine and the chlorine are both -1. So that means charge can't be affecting us. So that means we need to look at size. And the stronger lattice energy is the one with the smaller size. So compare lithium to sodium. Well, lithium is higher on the periodic table, so it's going to be smaller. And fluorine is higher than chlorine, so fluorine is going to be smaller, which means lithium fluoride wins this little battle. Between iron 3 oxide and manganese 4 oxide, the iron is going to be a +3, oxygen's a -2. The manganese is going to be a +4, oxygen's still a -2. Now looking at these, I see my oxygens are the same. My iron actually has a lower charge than my manganese, so it's going to be manganese 4 oxide because of charge. And then lastly, we have calcium oxide, +2, -2, and calcium chloride. Well, the calciums are the same, but oxygen has a higher charge than chlorine, so calcium oxide is going to win because of charge. And actually, there's another reason that calcium oxide is going to win. Oxygen is in row 2, chlorine's in row 3. So that means chlorine is significantly bigger than oxygen. So calcium oxide also wins because oxygen is smaller. You love it when the little guy wins, right?